To represent motion in physics, we need to make use of correct terminology, units, diagrams, and graphs. In this video, I will go over position, velocity, and acceleration versus time graphs. Let's say we have a stationary object. Let's see how we draw the xt, vt, and at graphs. This one is easy. So the object is stationary. The object is not moving, which means that the object over time only has one position. So xt would be just a straight line horizontal to the t-axis. And since the object is not moving, the velocity is 0, so we have a line on the t-axis. Since the object is not moving, the acceleration is also 0. What if the object is moving, but it's having a uniform motion? It does not have an acceleration, it only has a constant velocity. The xt graph is just a straight line. The position is changing, but it's changing in a constant manner because the velocity is constant and the slope of this line stays the same over time. In the VT graph, we have a horizontal line parallel to the t-axis. And for AT, again, because we have a uniform motion, we have no acceleration, we have a horizontal line on the t-axis. Now, the third situation is if we have constant acceleration. In this situation, the velocity is increasing over time constantly. For xt, we're going to have a curved line. Slope of this line is gradually increasing over time, meaning that the velocity is changing and increasing over time. And for the VT graph, we're going to have a straight line, which is showing the constant acceleration. And for the acceleration time graph, obviously, we're going to have just a horizontal line. We can find velocity from the position time graph and vice versa, and we can find the acceleration from the velocity time graph and vice versa. Let me show you how. The slope of the position time graph gives us velocity. This can be deduced by referring to the straight line graph equation. So what is the straight line graph equation? Y equal mx plus b. Y is actually x, right? So this would be x equal m, the slope, times x now would be t plus x0, or the initial position. So from here, m, or the slope, would be del x over del t. So this is, we know that this is the equation for average velocity. So from here, we could derive that average velocity is the slope of the xt graph. And we can prove the same thing for the VT graph. So the slope of the VT graph is also acceleration. But what if we want to find the instantaneous velocity? So, for example, if I want to find the average velocity between these 2 points, I will draw a straight line between them and then find the slope, and that would give me the average velocity. But if I want to find the instantaneous velocity, then I have to choose one point on this graph and then draw a tangent line to this graph. And then I'll find the slope of this tangent line, and that would give me instantaneous velocity. But how do we find change in position from the VT graph or change in velocity from the AT graph. The area under the curve in the VT graph is actually equal to change in position. This is very easy to see because if I want to find the area, I have to multiply this by this leg. So this is actually V and this is actually T, and the area is equal to VT, and we know that VT is actually del X. So from here, we could prove that the area under the curve of VT is actually change in position. It's the same here. We want to find the area of this shape. Again, this is A, this would be T, and the area is A times T, and we know that this is del V. I hope this helped you to understand how you can draw XT, VT, and AT graphs for different situations, and how to find acceleration from the VT graph, velocity from the XT graph, and vice versa.